this video I will explain the principles of a mass spectrometer. So a mass spectrometer is a device designed to determine the mass or individual atoms or molecules. A mass spectrometer is very useful to find out the formula of an unknown substance. It's also used by chemists that what they want to make sure that they have actually made the substance they were supposed to make. So it's very useful analytical technique, one of the most powerful ones. So there are 4 stages to a mass spectrometer, and the type of mass spectrometer that I will describe is called time-of-flight mass spectrometer, so TOF. Okay, so there are 4 main parts to describing how a mass spectrometer, a TOF mass spectrometer works. Ionization, followed by acceleration, flight or path, and detection. So a mass spectrometer simply can be represented like this, where it, as in the name suggests, it has mass, but what's actually measured by the mass spectrometer is the mass to charge ratio, right? And then if the charge is 1, then the mass to charge ratio equals the mass. So the mistake that candidates make is that they say a mass spectrometer is used to it measures the mass. No, actually it measures the mass to charge ratio. That's what we need to say, otherwise what we're saying is wrong. We use that mass to charge ratio to determine the mass, but a mass spectrometer gives us the mass to charge ratio. So it deals with ions, okay? And it deals with ions because then those ions can be, since they are charged particles, they can be accelerated by an electrical field. The whole setup is under vacuum, okay? And that's to prevent any contamination. Yeah, you don't want anything from the air to contaminate the and mess the measurements. Initially, before anything happens, before the ionization happens, we need to have a vaporized sample. So the sample needs to have been turned into a gas, and that's to prevent any interaction between the particles. So all the particles, all the molecules, or the atoms, if we are measuring isotopes, they are free from each other, so they are free from any interactions. Then ionization can take place. Okay, so there are 2 ways to ionize our sample. One is called electron impact, and the other is called electron spray ionization. So electron impact works by basically bombarding the gaseous sample, yeah, our sample that's turned into a gas, with electrons, and these electrons will take 1 electron from the sample. So we've got a gaseous sample, which is a neutral substance, not charged. We take 1 electron from it and we turn it into a positive ion. Okay. Usually this is how it's written. When we want the equation for the ionization, this is what we write. Okay, so basically our sample gaseous, by losing an electron, turn it into a gaseous ion, and it's that gaseous ion that can be then accelerated by an electrical plate. Okay, so one of the questions to say, why does it need to be an ion, is because then it's the charged particles that can be accelerated by an electrical current. The second method for creating a positive ion is called electron spray ionization. So the sample is dissolved in a very volatile solvent, usually water or ethanol or methanol, and injected through a really fine needle, and then it creates an aerosol, a mist, right? And the tip of the needle is attached to the positive terminal of a high voltage power supply, so the particles are ionized by gaining a proton, H+. Okay, and that's obtained from the solvent. That's why they use water or methanol or ethanol, because these are called protic solvents. So at the end, you've got your ion created like this. So we've got a gaseous sample, and it gains a proton, so it turns into a positive ion, and that can be accelerated. Okay, so what is detected here is the mass to charge ratio, but +1. It's the mass +1 to charge ratio. So that's what we need to take into account. We'll need to take away 1 from the measurement. Okay, so it's also one of the questions that's often asked by the examiners. So they rarely ask you to describe these methods, but it's quite useful to be able to describe them, because it helps us to understand how it works. So once the ionization is obtained, yeah, we use an electric field and of known strength, so that all of these ions are given the same kinetic energy. So all these ions are given the same kinetic energy. So here, if we have a mixture in our sample, then we create a mixture of ions, and all of these ions will be given the same kinetic energy. And that's very crucial, because as all the ions are accelerated, given the same kinetic energy, then they enter the flight path, so basically where they're allowed to drift, right? And that's how these ions are going to be separated, because since they are all given the same kinetic energy, that kinetic energy also depends on the mass. So ions with a greater mass will travel slower, will take them longer to travel through the flight path. So that's how these ions can be separated. So the time, since the lighter ions travel faster, yeah, the time that is taken by the ions will be proportional, or indirectly proportional, should I say, to their mass to charge ratio. So the element of time, that's going to be converted to a mass to charge ratio by the time it reaches the detector. So basically, we need to remember that heavier ions will travel more slowly than the lighter ions, and that's how these ions are separated. Okay. So here's an example. If we have like a mixture of isotopes of magnesium, for example, the 3 isotopes, 24, 25, and 26, they've all been accelerated. They're all given the same kinetic energy. So the lighter ions will travel faster, and they'll eventually be separated. Okay, so when they reach the detector, the lighter ions will reach the detector first. So how are the ions detected? Well, the ions then, they pick up an electron from the detector, and that creates a flow of electrons, and that's a flow of electrons in electrical current. So the greater the flow of electrons, the greater the current, the greater the abundance of that ion. And its mass to charge ratio is determined by the time that it has taken to travel. detection, the positive ion, it's a negative charge electric plate, and that generates a flow of electrons, an electrical current, and that's how it's measured, as I explained. Okay? And the size of the current gives the measure of the number of ions hitting the plates. So it gives a measure of their abundance, how much of that particular ion there is. So as I said a few minutes ago, the mass spectrometer measures the mass to charge ratio, and depending on the type of ionization, if it's electron spray ionization, then we need to remember that it's the mass plus 1 to charge ratio that is given, so we'll need to take 1 away. Okay, so it's really important to be able to rearrange this type of equations. So here we've got kinetic energy equals half mv squared. That's a famous equation that some of you might remember from the physics exam. And so all of the ions are given the same kinetic energy. So that's how we can find out their mass. And we need to remember that the mass needs to be in kilogram, and it's the mass of one ion. So we'll need to divide that 52 by 1,000 to get it, because it's 52 grams, and by to get it in kilogram, and that will be the mass of 1 mole of ions. So we'll need to divide, to find the mass of 1 ion, we need to divide also that number by Avogadro's number. So if they give you 52, you need to divide 52 by 1,000 and divide it again by the Avogadro's number to find the mass of 1 ion in kilogram, and that's that mass of 1 ion in kilogram that you need to put in that equation. Okay, so they will give you, they'll ask you to calculate either the distance traveled by the ion or the time. So it's very important that you get some sense of units. So for example, if you found a distance greater than, for example, a couple of a meter or meter and a half, or between 1 and 2 meters, that would be fine. But if you found like 200 meters, that would mean the apparatus is 200 meters long. So that should tell you, oh, you have made a mistake. Or that if you find that the time travel in the mass spectrometer, or the speed that you find out in the mass spectrometer is faster than the speed of light, which is 3 times 10 to the power 8 meters per second. If you find a number, velocity greater than 300 million meters per second, then you know you've got it wrong. So it's really important to get an idea of the range of these measurements. Thank you.